Hello there! This lecture is all about z-scores. And z-scores are basically derived with a very simple formula where the formula gives you a value, the z-score, that tells you how far away any given score is from the mean in terms of standard deviations. Or in other words, how many standard deviations above or below a score is from the mean. And we'll get into why that's an important value to look at because it tells you how extreme or unlikely or common a score is in any given data set. Also, when you convert values into z-scores, you're able to compare any given score to any other score, either within the same distribution or from totally different data sets. And you can compare them equivalently, even if they're coming from different distributions. That's why it's called a standardized score. It's because once you convert an X value into a z-score, you can compare z-scores across all kinds of different distributions. So we'll get into that as well. Also looking at some practical examples of when z-scores would be a really effective way to make decisions.
So now let's get into kind of the concept and what a z-score tells you, and then we'll look at some formulas as well. So as I mentioned earlier, a z-score tells you how many standard deviations above or below the mean a particular score is. So there's two pieces of this information. One is how far away is the score from the mean in terms of standard deviations, or how many standard deviations away from the mean is the score. And the other piece is like the direction. Is this above or is this below the mean? So the distance, again, is kind of the numeric value of that z-score, the absolute value, where you're going to ignore positive or negative values and just look at the number itself. That number tells you how many standard deviations away your score is from the mean. So for instance, if your mean was 100 and you had a score of 110 and your standard deviation was 5, then you would have a situation where you'd have a z-score of 2. Because 110 is 2 fives, right? 2 standard deviations above that mean of 100. If you had, again, a mean of 100 with a standard deviation of 5, and let's say that you had a score of 90, well, that would be a negative 2 because you're working with a score, 90, that's 2 fives, 2 standard deviations below now the mean of 100. So that numeric value, that 2, would tell you both the 90 and the 110 are 2 standard deviations or 2 fives away from the mean. So the larger the absolute value of that z-score, again, don't look at negatives and think that a negative means it's a lower number, right? Just look at the absolute value, just the number. The larger that z-score is, the further away from the mean that x value that it represents is. So when we talk about z-scores, those z-scores are a converted x value. They've been converted into a z-score. So a larger z represents an x value that's further away from the mean, more extreme, more rare. On the flip side, a smaller z-score, again, ignoring negatives and positives, just looking at the absolute value, just the numeric value, the smaller the z-score, the closer to the mean it is. And if you think about this as well, and when we look at the formulas, this will make a lot more sense. The z-score for the mean is always 0. So the further away from 0 your score is, the further away from the mean your score is, right? So the further away from 0 z is, the further away from the mean the x is. Then think about it again. The smaller, the closer to 0 your z-score is, the closer your x value is to that mean. Because remember, the z-score for the mean is always 0. Then we look at direction. So that's when you actually start to consider the positive or negative sign. So is this score above the mean, like the 110 is above 100, or below the mean, like the 90 was below 100? So again, like I said before, if the score is equal to the mean, the z-score equals 0. Remember, the z-score tells you how many standard deviations away your score is from the mean. Well, if your score is equal to the mean, it's no standard deviations away from the mean, right? It's equal to the mean, so your z-score would be 0. This score is 0 standard deviations from the mean because it's equal to the mean. If you have a score above the mean, that's going to be a positive value, a positive z-score. And if you have a score below the mean, you're going to have a negative z-score. So in the example that I talked about earlier, and I can write this down to make it a little easier to remember, if you have a situation where your mean is 100 and your standard deviation is 10, right? Okay, well, if we have a score of x equals 90, or no, I'm sorry, the standard deviation in my example was actually 5. So let's do mean equals 100, standard deviation equals 5, x equals 90, right? Well, that is 2 5s, 2 standard deviations. 2 times 5 is 10, right? 90 is 10 points away from 100. So 90 is 10 points, or 2 5s, below the mean of 100. So it'd have a z-score of negative 2. 2, right? 90 is 2 5s away from 100. Negative because 90 is below 100. If we had an x value of 110, the z-score would be positive 2 now, because 110 is 10 points, or 2 5s, above that 100. So it's above, so it has a positive z-score. So now when you see the formula, you will see that how that makes sense as well, right? So you could have, for instance, plugged in for x, 90, 100, that's going to give you negative 10, divided by 5, that's going to give you that negative 2. I wanted to show you how you could arrive at that conclusion with simple numbers conceptually before you rely on the formula. Now, the z-score for a sample is the exact same thing, essentially, just the notation slightly different. If you're working in a distribution of mean or sampling or sample scores from a sample, then the mean is going to look like x bar, and the standard deviation is going to be an s instead of a sigma. Same concept, though, same math. Now, you can flip that z-score formula to figure out, for any given z-score, I want to convert it back into an x value. And you'll see, just like before, the only difference between the sample and the population formula is the notation. So z-scores are very useful for comparing values within the same distribution to see how extreme or rare or common it is. So simply comparing a specific value to the mean is just not enough. Not only is it important to consider if a value is above or below the mean, but you also need to know how far away that score is from the mean in terms of how far most scores are away from the mean, or in other words, the standard deviation. So when we look at the z-score, it tells us how the actual difference between the score and the mean compares to the standard deviation. So how far away from the mean is this score in terms of how far away most scores are from the mean? If you have consistent scores with a really small standard deviation, even a slight variation from the mean between x and the mean is going to be less expected and more extreme than if you have a situation where you have very inconsistent scores with a large standard deviation. Well, that means that many scores are far from the mean, so a slight variation is pretty expected and likely. So when you have a smaller standard deviation, any difference from that mean is unexpected. It's more unlikely because most scores are close to the mean. But again, when you have a large standard deviation, that means your scores are more spread out, there's more variation. That means that if you get a score that's different from the mean, it's probably not that extreme or unlikely because there's a whole lot of scores that aren't the same as the mean because your standard deviation is really large. Now, there's a couple of criteria to just kind of roughly talk about, which scores have which kind of characteristics. So if you end up with a situation where you have an x value that is within one standard deviation of the mean, so for example, and when we were talking about a mean of 100 and a standard deviation of 5, basically anything from 95 to 105. Right? Because that's going to have a z-score of -1 and a z-score of +1. That's going to be a very common score in that data set. Most scores are about 5 points from the mean. So just knowing that, any score that's within 5 points of the mean is within most scores. Now, if we think about more extreme scores here, then that means anything that's 2 or more standard deviations away from the mean. So that would be extreme or rare. So if we think about this, remember, when we had our mean of 100 and our standard deviation of 5, well, what score was 2 standard deviations below the mean, right? 2 times 5 is 10, and so 100 minus 10 would be 90. So z of -2 would have an x of 90. And then on the other side of that, right, the higher end, okay, so x and z. So for z of positive 2, you just take 2 times 5, 10, add that to 100, right, because now we're looking at the positive end, higher than the mean, and you get that 110. So extreme scores would be 90 or lower, or 110 or higher would be extreme scores. Very unlikely in this data set. So remember, like I just showed you, if you have an x value that's within one standard deviation of the mean, it's going to have a z-score between -1 and 1. It's going to be a common value. But if you have a x value that's 2 or more standard deviations away from the mean, it's going to be extreme. And that's really any x value that has a z-score of -2 or below, or +2 or above. So here's another example. IQ scores do have an average or a mean of 100 with a standard deviation of 15. So based on that, you know that most scores are from an 85 to a 115. And if that doesn't intuitively make sense, you can use the formulas to figure that out, right? So you see here's this X formula that I showed you at the end of that 2 slides ago. You'll see here is that standard deviation. Here is my 2 z-scores of either -1 or +1, because remember we need to account for this one and this one. So you plug those in. On the low end, you get -15 plus 100, which is 85. On the high end, positive z, +1, 100 or 15 plus 100, you get 115. Let's look at another example when we look at extreme scores. So extreme scores are going to be anything 70 or lower or 130 plus. Take a second to look at the mean and standard deviation and see if that is making sense to you before we look at the formula. I always want to try to have you conceptually understand it before you have to rely on the formula and the math. All right, so here we can see extreme IQ scores are anything 70 or lower, 100 or 130 plus, because now we're plugging in a -2 z-score for the low end here of extreme scores and a +2 z-score for the high end of extreme scores using this X formula. So now this becomes -30 plus 100, which is 70, and then +30 with the positive z-score plus 100, which is 130. Now, IQ scores are on a normal distribution, so I'm going to show you visually what this looks like and why these z-scores are rare. So this represents our frequencies, right, from no values to a high number of values. We're not going to be specific here. Okay, so the shorter the curve, the more rare, the fewer those values there are. The taller the curve, like here, the more common, the higher frequency those values are. So if we talk just about X values here, our midpoint is our 100. That's our mean. And the z-score for our mean is always 0. So now let's sketch out our -1 z-score and then our -2 z-score. And on the other side, +1 and +2. So remember, for a z-score of 1, we figured out it was 115. For a z-score of +2, it was 130. Notice the z-scores are increasing by 1, so the x values are increasing by 15 because that's the standard deviation, and the z-score tells you how many standard deviations away your score is from the mean. Now on the low end, 100 minus the standard deviation was 85, and then 100 minus 2 standard deviations was 70. Now check this out. 100 is very common. It's the mean. And scores between 85 and 115 are also pretty common, right? A pretty high frequency part of the distribution. But once you get out to these 130 and 70 territory, all of these values to the left of 70 or 70 or lower, to the right of 130, 130 or higher, are very rare, right? They're in a low frequency part of that distribution. You're going to be working with normal curves and z-scores a lot in the future, so I just wanted to kind of preview what that's going to look like right now and also give you a visualization of common versus extreme scores. So remember earlier in the lecture I told you that z-scores are really useful for comparing scores within a single distribution. to figure out how extreme or common they are. Because it's not good enough to just look at the mean and go, oh, my score's above the mean or below the mean. You really have to consider, well, how far away is my score from the mean in terms of how far away everybody else's score is from the mean. And this couldn't be more relevant for you all than when it comes to quizzes. So I know that when I was in college, I wanted to know the mean and standard deviation for those quizzes to see how well I did compared to the rest of the class. So I'm going to do a demonstration that shows you how that information could be used. So for instance, if you got an 80% on a quiz, you'd feel pretty good about it if you found out that the mean was a 75, right? Because you're above the mean. Then if you found out that the standard deviation was 10, so let's look at that. Let's see how you would feel. So in this case, let's do our z-score to see how good we feel. So z equals x minus the mean divided by the standard deviation. So in this case, if the standard deviation was 10, mean was 75, so you got an 80 minus 75 divided by 10 equals 5 divided by 10 equals 0.5, and that's your z-score. So you'd be feeling pretty good about it, but you're still kind of within everybody else, right? Remember, most scores have a z-score between -1 and +1, and you're right there in the middle. So you did well, but a whole lot of other people did just as well as you. Now, what if you still had that 80%, but you found out that the mean was a 75 with a standard deviation of 2? Well, now let's do some math. Let's figure out what your z-score would be, even though this pen is being wonky. Here we go. So now you've got same numerator, 80 minus 75, right? You still did 5 points above the mean. So without knowing the standard deviation, you'd think, oh, I had the, same amount of performance compared to the rest of my peers. But now you know the standard deviation, how far apart most scores are from the mean. So in this quiz, most scores are between a 65 and an 85, right? Most scores are within 10% of the mean. But here, most scores are within 2 points of the mean. It's more consistent. So that means most scores would be from like 73 to 77. So when we have that 5-point difference, and now we're comparing that to a much smaller standard deviation, your z-score is really, really impressive. In fact, it's extreme, right? You did extremely well compared to your classmates. Like, wow, extremely well. And then here you did good, but not extreme. Okay, maybe I should write in cursive here. Okay, so if your goal is to do better or have a higher score relative to the rest of the distribution, you want a small standard deviation because it's easier for that difference between your score and the mean to be impressive because most scores are close to the mean. Now let's look at a situation where you did worse than the mean and see what the most desirable outcome would be. Like assume that your professor grades on a curve with z-scores. In this class, you would have a 0.5, but in this class, you would have one of the highest scores in the class. All right, let's take a look at the next one. So if you got an 80% on a quiz, you'd feel pretty good about it until you found out the mean was 85, assuming you care about social comparison or the instructor was curving the grades. So if you found out that the mean was 85 with a standard deviation of 10, here's what this would look like. You're going to see the math is going to look somewhat similar here. So you've got your score minus the mean of all scores divided by the standard deviation. So now your score is still 80, but now the mean is 85, and here our standard deviation is 10. So now you've got a -5 divided by 10, and so your z-score is a -0.5. So here, you're like, man, I did worse than the mean, so not great. But in this case, you don't want to be extreme, right? You're with everybody else, so you're still in good company. So you didn't do better than the mean, but lots of others did just as well or as poorly, if you, depending on how you look at it, as you did. So in this case, you would kind of want a bigger standard deviation because you want more spread so that your score that's lower than the mean isn't that surprising or rare. Now let's look at this other one. You've probably noticed a pattern here. These are both the same distance from the mean, but one's going to be negative, one's going to be positive. But we're going to be redundant with our math here just to demonstrate it. So here we go. We've got our 80 minus the 85 mean now, divided by the standard deviation of 2. That gives you negative 5 divided by 2, which is negative 2.5. So if this was the distribution, you did extremely worse than the rest of the class. Granted, you should still be proud of your 80%, but not if the instructor's grading on a curve, right? The instructor could be like, well, lots of people did well, so you didn't do as well as everybody else. You get a crappy grade. Here's your crappy negative 2.5. So just to demonstrate how not just comparing a score to the mean, but also to the standard deviation is going to tell you how extreme it is. And if these were on a normal curve, you could kind of sketch it out and you would see that this one would be way far to the right in the tail, and this one would be way far to the left in the tail, and both of these would be close to the middle. So now let's take a look at another example, remembering again kind of the criteria for what's common and what's extreme. So looking at our chase tellers again, Maria's mean transaction time was 99 and Bob's was 87. And in the population of tellers, the mean transaction time was 106.733 and the standard deviation was 24.941. So let's say the manager at Chase Bank wants to know, do Maria and or Bob have extreme transaction times within the population of tellers? Maybe they're going to target people with extreme transaction times with training or something. They're trying to make a decision. In the previous examples, the z-scores were relatively easy to determine without the formulas, but that's not necessarily always the case. So here's where these formulas are going to be extremely useful. So let's go ahead and start with the z-score for Maria. That's what that little subscript M represents. So using that same formula as before, x minus mu, or the actual score minus the mean, divided by the standard deviation, equals, okay, well, Maria's transaction time was 99. The mean of all transaction times was 106.733. And we're dividing that by the standard deviation of 24.941. So we have to solve for the numerator before we can do our division here. So 99 minus 106.733 gives you negative 7.733 divided by, again, that 24.941. And this gives you negative 0.310 is your z-score. Is that extreme? No, not extreme. All right, let's take a look at Bob. Oh, not an M. B for Bob. Using the same formula, x minus the mean divided by the standard deviation. So Bob's transaction time was 87 minus 106.733. Notice, since we're looking at the same distribution, the mean and standard deviation are going to be the same, right? We're looking at the same population of tellers, but the x value is different because now we're looking at a different teller. So 87 minus 106.733 gives you negative 19.733. So on the face of it, it looks like, Bob has a way lower transaction time than average, right? Well, is that super extreme compared to how far apart most transaction times are from the mean, that 24.941? Not so much, right? His z-score is only negative 0.791. So his z-score is also not extreme. So again, it's important to not just look at how the score compares to the mean, but how does it compare to the mean in terms of how far apart most scores are from the mean. So let's say that the manager at Chase Bank doesn't want to convert everybody's mean transaction time into a z-score, and they really just want to look at what specific transaction times would put you in the extremely low or extremely high end. So in this case, you could use the X formula to figure out, okay, so which transaction time would represent the low end of extremes, right? Or that would have a z-score of -2 or below. And then on the high end, which transaction time would represent the extremely high end scores that would have a z-score of 2 or above. So let's just use the X formula to figure that out. So X equals z times the standard deviation plus the mean. So in this case, if we're looking at the low end of extreme scores, we could pop a -2 in for that z-score. So -2 times our standard deviation of 24.941 plus our mean of 106.733. Let's take a look at this. The z-score tells you how many standard deviations away your x value is from the mean. So by taking the z-score and multiplying it by the standard deviation, it then tells you how many points away your score is from the mean. So then when you add that to the mean, you end up with the x value. Because we're working with a -2 here, we're going to end up with an x value that's below the mean, which is what we want because we're looking at the extreme low end. So when we start to work through this math, solve for our multiplication first, and -2 times 24.941 is -49.882 plus our mean of 106.733. And we end up with an x value of 56.851. So any teller that has a transaction time on average of 56.851 seconds or lower has an extremely low typical transaction time. Now let's do the same thing for the high end, using the same exact formula, except now we're going to be working with a +2 z-score instead of a -2. So we've got 2 times 24.941 plus 106.733. This becomes basically, it looks the same, except now instead of having a -49.882, we have a positive plus 106.733. And we end up with an x value that's above the mean, which makes sense because we have a positive z-score, and we're looking at the high end now of extreme scores. So those scores would definitely be above the mean. So anybody with an average transaction time of 156.615 or higher would have extremely high transaction times. So let's look at a specific example where decisions could be made based on z-scores among these tellers. So in the past, the manager of Chase Bank would give raises to employees in the bottom 30% each quarter of transaction times and fired employees in the top 20% because they're striving for small, like short transaction times to get people through the line quickly. So if you're in the bottom 30%, you get a raise, but if you're in that top 20%, you get fired. But maybe instead of making percentiles the basis for raises and firings, you can use z-scores. Because when you're always firing the top 20% of transaction times, maybe they're all doing really well, right? They just happen to be in the top 20%. So you're forcing yourself to fire people who are still pretty good performers, just not as good relative to the rest of the performers. Also, maybe if everybody's doing a crappy job, you're still giving raises to those in the bottom 30% of transaction times. So there you go. Raise, even if all are performing poorly, you still are going to give them a raise because you're forcing yourself to. The 30% always gets a raise. And then same thing with the firings. You don't want to force yourself to have to fire people, even if everybody's doing relatively okay. So a much better strategy for this would be to fire those that have a z-score greater than 2. So extremely high transaction times relative to the rest. You're not forcing yourself to get rid of a certain percentage of the workforce. And then maybe go easy on the raise a little bit and give a raise to anybody who's outside of that common transaction time on the low end with a z-score less than -1. So now you can see all of the tellers, not just Bob and Maria, and we're looking at all of their mean transaction times and how much how extreme their mean transaction time is to the rest of the transaction times among all the tellers. So you'll see I did that using z-scores. So for each of these, the z-score formula is going to look the same because we're working with the same population mean and standard deviation. The only thing that changes from one teller to the next is the x value that comes from this column right here. So you'll see for Christine, her 124 transaction time minus the mean divided by the standard deviation. Do the math, she has a z-score of 0.692. So she's on the high end of common values. So you'll see all the z-scores in bold in that middle column here. And we'll see, okay, does anybody get fired? Well, in this case, no. Nobody has extremely high transaction times. Everybody is pretty relatively consistent. I think one of our highest scores was right here. Good old George with his 137. We've got a 142 here as well, right? That gives us a pretty high z-score. So you can see the higher the x value, the higher the z-score, right? But they're just not bad enough. They're not taking so long that they deserve to be fired, according to the manager. Who gets a raise? Well, we'll see that the lowest transaction times belong to Jake and Bianca, and that translates into them having the lowest z-scores, right? The most negative z-scores. So that's exciting for them. They both get a raise because they have low transaction times relative to the rest of the population. So now we're not forcing anybody to get fired. We're not just giving raises to the best 30% just automatically. We have a better system for identifying who's extreme and who deserves to be recognized with a raise. So we just looked at an example where we use z-scores to compare values, or x values, within a single distribution or a single data set from one group of people measuring the exact same thing. But z-scores are especially useful for comparing scores from different distributions. Think about it. It's impossible to compare values from different distributions, or in other words, from different samples or populations with different means and or different standard deviations. The values could be scored on different metrics. So for instance, a 45 out of 50 is not equivalent to a 45 out of 100. You may think that computing a percentage would overcome this particular difficulty of comparing values scored on different metrics. So for instance, you could convert that 45 out of 50 into a 90% and that 45 out of 100 to a 45% to compare them. But that still does not give you the ability to examine how extreme, common, impressive, or troubling even each score is among all the other scores collected on the same metric. This requires comparing each value to the mean and standard deviation of all values collected with that data. Z-scores allow you to standardize scores from different samples or populations, so you can make direct comparisons between scores that were not measuring the same thing in the same way. And you'll see that in this example here. So basically, by converting all your values into z-scores, you go from trying to look at apples and oranges to looking at apples and apples. You've converted everything into a standardized z-score, so you can compare different distributions. No matter what the original mean and standard deviation was for those scores, when you convert all those x values into z-scores, the mean for the distribution is always 0 and the standard deviation for the distribution is always 1. So that makes it a standardized score. You can compare, for instance, different scores from different metrics looking at different things equivalently. So let's say you were a cashier at Chase and you wanted to determine which performance metric you performed the best on. So they evaluate you based on transaction time, based on peer ratings of performance, and manager ratings of performance. Well, the best way to do that is to use z-scores to find out which areas you are the most or the least impressive in compared to your fellow employees. So let's do it. So if we're looking at the transaction time, to find your z-score, you do z equals, again, x minus the mean divided by the standard deviation. So in this case, your x value is a 99.267 minus 106.733 divided by the standard deviation of 24.941. So you end up with, in the numerator, negative 7.466 divided by 24.941, and you get a z-score of negative 0.299. So it's good, right? Because we want negatives, we want low transaction times, but it's not impressively low, right? It's good, but it's not amazing. So now let's take a look at pure ratings of performance, right? Now look, it would be impossible to compare this mean of 106 to this mean of 7, or this x of 99 to this x of 85, because we're not even looking at the same metric at all. But by converting them into z-scores, we're going to go to compare all of these values. Here we go. Z equals, same thing, x minus mu divided by standard deviation. So now we're working with a little bit easier numbers. You have 8.5 was your score minus the mean of 7 divided by the standard deviation of 1.5. So this equals 1.5 divided by 1.5, and you have a z-score of 1. So this is pretty good, but it's on the high end of most scores, right? It's great, but there's a lot of other people who did that well in terms of peer ratings of performance. Now let's take a look at the manager ratings of performance. So z equals x minus the mean divided by the standard deviation. Do yourself a favor if you haven't been doing it already. Pause the video right now and try to figure this one out on your own. You need to practice. Okay, so now we've got our 8 minus our 6.5 divided by 0.5. Okay, 8 minus 6.5 is 1.5 divided by 0.5. Notice that in terms of ratings of performance, your score was 1.5 points higher when it came to peer ratings and 1.5 points higher than the mean when it came to manager ratings. But how impressive that is depends on how it compares to the standard deviation. Well, before, that was within the range of most scores. But now, when we figure out our z-score, you're crushing it. That's a really extremely high z-score. Most people had ratings within about 0.5 points of 6.5 when it came to the manager's rating. So between a 7 between a 6 and a 7. So that 8 is really awesome. They really, really thought highly of you compared to the other peers. So I would say that your most impressive score would be the manager ratings of performance, which is great because that's probably the person who's going to be determining a lot of things about your job. So it's nice that they have such a high opinion of you. Now, just because I love z-scores so much and I want you to love them too, I'm going to show you another example where z-scores could be used to make decisions, and then we'll be moving on to your lecture quiz. So I'm just going to read this to you. So executives at Chase Bank tasked all managers in Clark County with participating in an outreach program to encourage community members to choose Chase for all home loans and car loans. So they're getting out in the community, they're trying to get people to get their loans with Chase. As an incentive, so to get the managers to participate, the manager with the most impressive number of new home and car loans in 6 months gets a $5,000 bonus. Now think about some of the issues that could arise if you were just basing it on who had the most loans or the highest number or the most amount of loans in all the different areas of Clark County, how that could be problematic. Clark County's huge, right? So here you go. The executives do not want to simply award the bonus to the manager whose branch had the most loans because, think about it, That's really going to unfairly advantage managers in the more affluent or wealthy areas and or the more populated regions. If there's more people, you have a better chance of getting more loans. If people have more money, you're going to have a better chance of encouraging people to buy a car or a home through Chase. If there's not very many people or people are pretty broke, chances are, no matter how good your campaign is, you're not going to get people to get home or car loans. So the manager doesn't want to unfairly advantage those managers who are in more populated or more affluent areas. So the executives are going to use z-scores to determine how well each manager performed relative to the other managers from branches in the same region. So now they are looking just how did you do compared to the others in your region, not compared to everybody in Clark County because that's unfair. So the manager with the highest score within their specific region that has the same kind of population and affluency, they're going to get awarded the bonus. So now let's take a look at that data from those different regions that have Chase branches in Clark County. So if you see here in this table, this mean represents the total number of loans for branches in that region divided by the total number of branches in the region. So on average, how many loans, home and car loans, did branches get in these different regions that are represented here? The standard deviation tells you the typical difference in the number of loans among the branches in the region. So in Enterprise, on average, they were getting 33 home and car loans in the past 6 months, and most branches had within 7 loans of that. So if you think about it, 33 minus 7 would be 26. 33 plus 7 is 40. So most branches in Enterprise got 26 to 40 loans, home and car loans, in the past 6 months. So if you look at this, look and see how unfair it would be to give a manager a bonus based on raw number of loans. A manager who put forth a ton of effort in Laughlin, right here, they're working really hard, they're trying to get people to get loans there. They are really not going to stand a chance against a manager who put forth zero effort in Las Vegas, where there's a ton more people that could be potential loan getters, and they also have a higher median income. So to combat that problem, we're using those z-scores. So remember, a higher x value, or even the same difference between an x value, a score, and the mean, does not necessarily equal a higher z-score relative to the other branches in the region. If we look at Jade, those 55 loans seem quite impressive compared to Louise's 20 loans in her branch. But when you take into account the fact that most branches in Vegas got around 50 loans with a standard deviation of 14, that z-score is mediocre. Like, meh, it's all right. It's pretty common. It's not surprising. But when we look at Louise, she's in Laughlin. Those 20 loans are really impressive compared to the average of 12 in her region and that small standard deviation of 4, right? Here in Laughlin, most branches are getting between 8 and 16 loans, right? 12 plus or minus 4. So that 20 is way beyond that range, and that gives her a really extreme positive z-score. Yay! So I didn't demonstrate all the possible branches and all the possible managers, but you can see how the manager, how the executive could use that data to fairly give the bonus to a manager based on how well they did relative to the other stores in their region, not just across the board raw data.